Welcome to our podcast, everyone. Today, we're diving into the fascinating world of mixed iron-nickel oxides and their role in electrocatalysis. With us are two experts in the field, Kimberly and Geraint, and we also have Matthew, who will be guiding us through some of the complex science.
Hey, Joanna. I'm excited to discuss this. The topic is very important, especially in the context of renewable energy solutions. The oxygen evolution reaction, particularly, is a crucial part of hydrogen production.
Absolutely, Matthew. The oxygen evolution reaction is key in electrolytic water splitting, which is one way to produce hydrogen sustainably. Mixed iron-nickel oxides have shown promise in improving this process.
Right, and what's interesting is how these mixed oxides outperform their pure metal counterparts, especially around that magic 10% iron content mark.
That's intriguing. Let's back up a bit. Kimberly, could you explain why the oxygen evolution reaction poses such a challenge in the production of hydrogen?
Sure, Joanna. In simple terms, the oxygen evolution reaction involves several steps that have high energy barriers. This makes it difficult to drive the reaction efficiently. The extra energy lost during this reaction translates into heat, which decreases the overall efficiency of hydrogen production.
And traditionally, noble metals have been used because they're effective, but they're also expensive and not ideal for large-scale applications. That's why there's a big push towards using more abundant and cheaper metals like nickel and iron.
Exactly. Under alkaline conditions, these base metal oxides perform reasonably well, albeit with room for improvement, which is where our mixed oxides come into play.
So if I understand correctly, these mixed oxides, particularly around 10% iron, showcase significantly better electrocatalytic activity than either pure nickel or iron oxides. Why is that, though?
That's partly due to the formation of a spin-L phase called nickel ferrite, which appears to be quite effective in facilitating the reaction. It's like finding the right rhythm in a dance. Once everyone is in sync, everything flows much better.
And the synthesis methods influence this. They range from evaporation-induced self-assembly to hard templating and dip coating, each offering different outcomes in terms of surface area and composition consistency.
These different methods impact how the iron is integrated into the nickel oxide structure. From what I've seen, the dip coating method seems to offer the best results due to direct electrical contact with the conductive mesh, without any blocking components from inks.
Fascinating. Now, let's talk about these advanced characterization techniques. I hear they played a crucial role in understanding the materials better. Could you shed some light on that, Kimberly?
Absolutely. Techniques like Raman spectroscopy and X-ray absorption have been pivotal. They're like detectives that piece together clues about the electrocatalysts' structure, identifying phases like nickel ferrite and assessing the oxidation states of the materials.
The Raman spectroscopy, for example, can detect crystalline nanoparticles and amorphous phases, which aren't easily detectable by other methods. It's essentially uncovering hidden layers of the catalyst's identity.
And don't forget X-ray absorption, which reveals details about oxidation states and coordination environments, helping us understand why these materials perform the way they do under different conditions.
This really highlights how crucial advanced characterization is in revealing the story behind the catalyst's enhanced activity. Speaking of performance, how do these insights translate into real-world applications?
Well, understanding these catalysts better means we can design more effective ones. Improved efficiency in water splitting could significantly lower the costs of hydrogen production, making renewable energy more viable globally.
Indeed, and by optimizing electrocatalytic activity, these developments could pave the way for industries to adopt greener technologies, which is a step toward addressing climate change.
Plus, it's not just about the energy sector. Enhanced catalysts have implications for a wide range of industries that rely on oxidation reactions.
It's impressive how these small-scale scientific nuances can have large-scale societal impacts. As we wrap up, what are some key takeaways our listeners should remember about Fe₄O₄ catalysts?
Mixed iron-nickel oxides are powerful players in advancing electrocatalysis for alkaline electrolysis due to their higher activity levels compared to pure oxides.
Exactly. The synergy at around 10% iron content illustrates a sweet spot for electrocatalyst effectiveness, and this could lead to more economical renewable hydrogen production.
And let's not forget the role of advanced spectroscopy techniques. They've given us deeper insights into the structural and functional aspects, guiding future innovations in the field.
Thank you, everyone, for the engaging discussion. We've uncovered some intriguing insights today, bridging the gap between detailed scientific research and its potential real-world applications. Until next time, keep exploring and questioning the world around you.